In this video, we're going to talk about the idea of infinite limits. So this is where a limit should, in some sense, equal infinity. And at the start, I want to emphasize the fact that this is a case of limits that don't exist. So in particular, this limit does not exist, but when it doesn't exist in a certain way, we can more specify the behavior of this limit by saying that it equals infinity in an appropriate sense. So we're being more specific than a limit not existing when we say it equals infinity. Let's start with an example. If we look at, say, x going to 0 of 1 over x squared, what's the graph look like here? Well, the graph here is going to be something like this. The function is sort of taking off upward as I approach in towards 0. It's 1 over x squared, so it's always positive. As x gets really, really small, the y value gets really, really big. So there is no number that this function approaches as x goes to 0. So limit x goes to 0 of 1 over x squared does not exist. But we also have this statement down here. The y value gets large no matter how we approach 0. We can be more specific as to what's actually happening here beyond just the limit not existing. The point is that both sides of the function are getting very large, in fact, larger and larger and larger, and staying positive as x goes to 0. This would be a case where we could say the limit, it doesn't exist, but if it did exist, it would be infinity. It's getting bigger and bigger without bound as x approaches 0. It's because in some sense the function is approaching infinity as x goes to 0, and we can talk about that in a limiting sense. So our definition here is the following. We say limit x goes to c of a function f of x equals infinity if, as x approaches c, f of x gets bigger and bigger in a positive sense without bound. As in, it doesn't sort of stop anywhere of getting bigger. It doesn't like flatten out somewhere really, really high up. It just keeps getting bigger and bigger and bigger without bound as we get closer to 0. Similarly, we say limit as x goes to c of f of x equals minus infinity if, as x approaches c, the values of f get more and more negative without bound. And as a follow-on point, we can also use these to talk about one-sided limits as well. So I can say limit from the right is infinity, from the left is infinity. All that stuff also works with this notation here. But again, these limits don't exist. So our limit laws do not apply to limits that equal infinity. We'll look at one more example along this front. Here's the function 1 over x minus 1 cubed as x goes to 1. What's different here? Well, the difference here is that if I look at x equals 1, which is the problem, x equals 1 is the problem here. If we look at that point, I would say for x bigger than 1, this value is small and positive, so it's going to look like this. But for x less than 1, x minus 1 is negative, and cubed keeps negative. So that's going to look something like this. So in this case, again, limit x goes to 1 of 1 over x minus 1 cubed does not exist. And it still doesn't exist no matter what. I can't say anything about plus or minus infinity here, because the difference is on one side it's going up, on the other side it's going down. What we could say about this function is that limit as x goes to 1 from the left of our function is minus infinity, because as I come in from the left side, I'm going to minus infinity down this way. And limit x goes to 1 from the right of our function is plus infinity. Come in from the right, I go up to plus infinity. So these two do not match, even in their not existing bit. So I can't say anything about the full limit as x goes to 1 of this function. So no matter what happens here, any case where things go to infinity is called a vertical asymptote. You've seen this idea before. It's usually things where a rational function is not defined or has a 0 in the denominator. But this is the same idea, because if that is the case, then we will have exactly that at that point, the limit of the functions go off to plus infinity, or minus infinity, because that's how things work with rational functions. So the same thing you're looking for that you saw in previous classes, looking for vertical asymptotes by looking at the zeros of the denominator, but we can also define those things in terms of points where we have limits of a function that go off to infinity. So that is the idea of limits that are equal to infinity in the appropriate sense defined here. The limits don't exist. We can use this equal infinity notation to be more particular about the behavior of these limits as I approach these values. We're not saying we can actually do things with these limits. They still equal infinity, they still don't exist, but we can be more descriptive as what's going on by using this notation of limits equaling infinity.